Okay, so I was asked to talk about the history of the chiral anomaly. I'm going to follow to some extent, to a great extent, my write-up in Adventures in Theoretical Physics, volume 37, published by World Scientific. But I thought that actually had a predecessor, which is a paper on arXiv in 2004 called Anomalies to All Orders. And what happened was, after we moved back into the new Bloomberg Hall, Frank Wilczek had invited Gerard de Hooft as a visitor. And one day he popped into my office and said he was preparing a book called 50 Years of Yang-Mills Theories and wanted to know if I would contribute an article on anomalies. And in particular, he wanted me to touch on the controversies with Roman-Jackiw, which you saw figured in that Physics Today letter. So I said yes, and I wrote an article, a long article. I decided to focus not just on anomaly history, which I did in the article, but also on the all orders calculations of both the chiral anomaly and the trace anomaly. And then there's a section on supersymmetry and some of the issues that arose from non-renormalization theorems of supersymmetry. Now, what's in the Adventures in Theoretical Physics is essentially pretty much the same thing that's in this article for Gerard's volume, but minus the discussion of supersymmetry and adding a discussion of corrections to scaling corrections to the Collins and Mansfield equation and other things that I did with Wu-Ki Tung. So what my talk will be will more closely follow the Adventures in Theoretical Physics version. Now, that came about in the following way. After the anomalies to all orders, which I'll hold up here, the arXiv number, I'll read it off, is HEP-TH /0405040. So again, it's HEP-TH 0405040. After that appeared, there was a review in the CERN Courier by a couple of years later, let me see, November 2005, by Ian Aitchison of Oxford. And he said some nice words about my anomaly article in the course of the review. And KK Fuad, the boss at World Scientific, picked up on that and then asked me to write a book or something. And there was some back and forth with him and his editors. And what ended up was a volume of reprints plus commentaries. So I sort of selected reprints with a detailed historical section of commentaries at the very beginning of the book. So that's what's in the Adventures in Theoretical Physics. And I'll follow the commentaries. The articles are all printed in the book as well. Okay, so now let me go to the anomaly story. I didn't set about discovering the chiral anomaly. At the end of the Adventures in Theoretical Physics, there's a little section where I say kind of what next. And what I point out is that most of the significant things I've done have come out as offshoots of other calculations and were not the intended product. This has happened a lot. It's happening even now with my current work on gravastars and galaxy formation, where I started with A in the gravastar papers and I've ended up with something quite different. I might mention a bit of that at the end, but this has been a pattern throughout my work. So I got into anomalies when I was a junior fellow at Harvard before a visit to England. I was thinking about trying to account for the muon mass by making the muon have an axial vector coupling to a gauge boson with a magnetic monopole coupling, that somehow the magnetic monopole strength would get renormalized to zero, unlike CVC for vector currents, where the vector charge coefficient is renormalized to 1. There's no renormalization. And I spent a month or two fooling around with equations for the vertex part of the axial vector current and got nowhere. Somewhat to my embarrassment now, I'm thinking about it. At one point, I went to George Carrier, who was a famous applied mathematician at Harvard, and showed him what I was doing, and he didn't have any helpful comments, which is right, because it was silly and I was really wasting his time. Anyway, when I got to the UK, I was invited by Richard Eden to the Cavendish lab in the UK for 6 weeks, I think. in April to May of 1978. I hope you're right. And it was a very nice visit. Let me just go back now and look at the book. Not 1978, it was 1968, spring of 68. So when I got there, I decided, well, I'm not getting anywhere with these vertex equations trying to get the charge of the monopole renormalized to zero. So let me try and answer a well-posed question, which is the axial vector vertex in QED renormalized by Z2, the standard wave function normalization? And that was a question that I could tackle by analogy with a very nice proof in Bjorkane and Drell volume 2, showing that the vector vertex is renormalized multiplicatively by Z sub 2. So I rather rapidly constructed a proof following what Bjorkane did in that second volume. And it relied on using the Ward identity for the axial vector current, the formal Ward identity. And I went through all the stuff. And at the end, it was quite straightforward for the non-closed loop diagrams, where the axial vertex is attached to an electron line. But where the axial vertex is attached to a closed loop, you had to shift integration variables in the closed loop to verify the Ward identity that you needed. And the Ward identity was needed to prove that Z2 was the only renormalization needed. So I had a formal argument there that worked, but then I decided, just to be safe, I better check the lowest order diagram, the triangle diagram, which is divergent, has divergences. That's the diagram where an axial vector vertex couples to an electron loop and couples to two vector vertices. Now, I knew this is sort of a stroke of good fortune from a graduate student journal club that I participated in Princeton in the early 60s. That one session was devoted to a paper by Leonard Rosenberg of Penn at that point. I have his paper here. Electromagnetic interaction. Is that visible? Electromagnetic interactions of neutrinos, in which he calculated the Feynman amplitude for the process of virtual gamma coming from a nucleus going plus a neutrino going to a photon plus a neutrino. And he did a careful calculation and reduced the whole thing to Feynman integrals. So there was nothing to do at that stage using his formula, like calculating shifts in Feynman diagrams. He did all the Feynman diagram stuff. And he, of course, since photons have to couple to gauge invariant vertices, he imposed gauge invariance, which eliminated the two divergent amplitudes in his calculation in terms of convergent amplitudes. So I had a concrete formula, and I tried the axial vector Ward identity and found, to my amazement, that it didn't work, that there was an extra term. So here I'll show some visuals. The top line is the vector current, psi bar gamma mu psi. And the next line is the axial vector current, psi bar gamma mu gamma 5 psi. And the naive divergence equation in spinor electrodynamics, which says that the divergence of the axial current is equal to 2I m naught, m naught is the bare mass, times the pseudo scalar current. So that's, which is psi bar gamma 5 psi. What I found, not in quite this form, but in momentum space form, is that there was an extra term of the structure epsilon mu nu lambda sigma, K1 lambda, K2 sigma, where the K1 and K2 are the photon momenta. So there was a funny extra term, and that was kind of surprising. I was rooming at the time in the Cavendish with Sam Treatman, my former thesis advisor. I mentioned it to him, and he said, what caused it? And I said, I'm going to find out soon. And a day or two later, I told him, again, basically from graduate student reading, the appendix to Rauch and Rohrlich's QED textbook discusses that if you have a shift in integration variable in a linearly divergent integral. Let me get some water. It's not, the result is not zero. There's a finite residue left over. And in this case, the finite residue just had the form of the extra momentum space term I was finding. So it's clear what was happening was that the formal derivation of the axial current conservation equation changed because you had to make this shift of integration variable inside a linearly divergent integral. Excuse me, trying to get my throat clear. Okay, so at that point, I had to leave England and go back to the US. So I knew there was something interesting going on, but I didn't want to write it up until I had the conversion to a field theoretical formula of the sort that I showed you. And that involved, of course, doing a careful calculation of going from momentum space back to coordinate space to get the operator form of the anomaly equation. One had to be careful with phases and signs, the usual stuff. And so by the end of the summer, I was at the Aspen Center for Physics that whole summer. By the end of the summer, I was also skating. I went out there because of physics and because of the skating coach I had was out there in the summer. So at the end of the summer, by the end of the summer, I had a manuscript describing the anomalous behavior, or it was called the axial vector vertex of spinor electrodynamics, I think. And it showed that there was an anomalous, I called an anomalous extra term in the divergence equation. So you had this funny extra term, alpha naught over 4 pi. Alpha naught is the bare fine structure constant, and then F mu nu times F mu nu dual, contracted with F dual. And this also had the consequence that it answered my question, is V2 the renormalization constant for the axial vertex? And the answer is no, that the axial vector vertex is normalized by Z sub A, which is Z sub 2 times 1 + 3/4 alpha naught over pi squared log lambda squared over n squared. There's an extra cutoff dependent factor. So in fact, Z2 does not renormalize the axial vector vertex in spinor electrodynamics. Now, just at that point, when that write-up was finished, Sidney Coleman arrived in Aspen. Of course, I knew him from Harvard because I'd been a junior fellow at Harvard. And it was rather memorable. This isn't in my write-up, but I mentioned this little whole anecdote at a conference that Sidney's friends ran for him at Harvard when he was very sick. And they had a lot of his people who work at Touch come in and tell anecdotes at the banquet and also visit him. And then there were a number of formal talks. So anyway, Sidney came. I brought him for dinner at Townhouse East where I was staying. And we opened the door, and my child Jessica came tumbling down the carpeted rug, all down the stairs, and landed at Sidney's feet. And Sidney looked down and said, "Now what have we here?" Anyway, Jessica was not hurt and appeared at this conference at Harvard much later with a photograph of herself at that stage of 18 months, maybe, and 2 years, I forget. And it was sort of a show and tell moment. So Sidney came up for dinner and then said, when I told him what I was doing, he said, "Oh, well, Bell-Jackiw found the same thing, that there's a anomalous term, but that it can be eliminated by putting in a extra scalar term that can be coupled to eliminate it." And I thought immediately that's going to cause other problems, and in fact then worked out what the other problems would be. But also from the Bell-Jackiw work, I learned about the Sutherland-Veltman theorem, which I had not known about before. And the Sutherland-Veltman theorem says that if you compute pi naught decay via PCAC, you get 0, because the term partial mu j mu phi, the divergence of the axial vector current, has an extra kinematic 0 that gives you a 0 result for pi naught to 2 gamma decay. So that made the whole thing very interesting, because the rather formal spinor electrodynamics calculation I'd done suddenly had implications for a physically measurable process. Now, what Bell-Jackiw did, and this, of course, was the source of all the much later controversy, they, at that point, making this very nice observation, then took a wrong turn, which was instead of saying, well, the anomaly then gives you the pi naught to 2 gamma, they wanted to restore PCAC, put in a regulator, which turned out to be spurious. It destroys renormalizability, so it's not the right thing to do. And they ended up never calculating the anomaly coefficient. So I analyzed all this. I had a dilemma since I had a complete manuscript. I wanted to be clear what I'd done before meeting Sydney and learning about Jackiw and what I did after I learned about what they did. So I wrote a long appendix to my PhysRev article, which discusses all the issues that arose after I was aware of the Bell-Jackiw work. And what I did was I showed that if you use the Sutherland-Veltman theorem and the anomaly equation converted now to PCAC, here's the PCAC version up on the top line, where the divergence, now I've used Murray-Gell-Mann's notation for the current, F3 mu 5. And the first term is the pion term, pion interpolating field. And the second term is the anomaly with a coefficient that depends on the charge structure of the couplings in your theory. So you have this coefficient S. And then I analyze that for various possible models for the charge structure. And what I showed in that appendix was that if you assume one set of fractionally charged quarks, the amplitude came out approximately 3 too long. But with several different choices of integrally charged quarks, you got the right amplitude. And with one of them, in fact, you got the right amplitude and the right sign. The sign was later analyzed by other people, and that's discussed in my Selecta article. So I just knew that the magnitude came out right with certain integrally charged quarks. Now, later, I showed in another paper that Ham-Bamboo quarks also gave the right everything. And that served later as a stimulus for the paper of Bardeen, Gell-Mann, and Fritsch, where they introduced color as simply a tripling of the number of quarks, which gave you the additional factor of 3 that you needed in the amplitude to get the right pi naught to 2 gamma decay. Now, there are other things that I did. Here I have to look at my Selecta article that were in the original version, the part before I saw the Bell-Jackiw paper and thought about pi naught decay. Let's see where it is now. Yeah. So I showed that, first of all, the axial vector renormalization is not Z2. That was answering the question I started with. I showed that it leads to infinite radiative corrections in certain calculations, but that you can cancel the infinity between different fermion species with the right choices of couplings. And so that was the beginning, in a very primitive way, of anomaly cancellation that figured, of course, much later in gauge theories. And then I also showed that the asymptotic behavior of the ABB triangle, because the anomaly saturates Weinberg's bounds rather than being 1 power better. And that always feeds into why the anomaly has to be canceled in gauge theories, because much later on, a number of people showed if you put back-to-back triangles, this extra power that's allowed by the anomaly term gives you bad divergences. So you have to cancel anomalies between fermion species. And then finally, I showed that you could still define a gauge invariant chiral generator. And this, in its non-abelian version, eventually played a role in the U of 1 story and Hithoof's nice solution of the U of 1 problem. Okay, so that was all in the earlier part of the paper, not in the appendix. The appendix was basically the discussion of what happens if you use the anomaly to calculate pi naught to 2 gamma decay by saying, I'll go back to this side now, but the matrix element by Sutherland-Veltman on the left-hand side is 0. So therefore, the whole matrix element of pi to 2 gamma comes from the anomaly term, and it relates it to the charge structure of the constituent. And then it gives you a way of getting at that. And so this is the formula. You get this unique formula to find out the 2-gamma decay amplitude is the inverse of the pion decay constant times charge pion decay constant times factors that are known, including this factor S that counts quark charges. Now that was the beginning of a long effort to show that the anomaly wasn't renormalized in higher order. Because if you can use the modified PCAC equation to calculate pi naught to 2-gamma decay, you better be sure that strong interaction corrections or other radiative corrections don't change the anomaly coefficient in the higher orders. All right, now in the meantime, I'd sent my paper draft to Bell-Jackiw, and they sent me back letters, one from Jackiw expressing doubt that you can do any unambiguous calculation, and one from Bell that said that he thought about adding a electromagnetic term to PCAC, but didn't quite see what to do to follow up on that idea. And so what they did instead was to restore the PCAC equation with CVC as well by putting a regulator. Now, I had those letters. Now, I had them in my files for many years. I'd actually forgotten about them. And at one point, I was reminded about them because Tianyu Cao, a wonderful historian and philosopher of science at Boston University, came to me and said that a footnote you wrote in your paper about the Bell-Jackiw paper doesn't seem to square with what you wrote in the body of the paper. And I said, well, the footnote was my being polite to Bell and who I revered in as a result of the letter he wrote. So I gave him permission to go down into the archive anti-room. We didn't have a proper archive at the IS at that point, and dig into the boxes. And they came up with these letters that I basically totally forgot about. So they are now in the Institute archives. We now have a proper archive room, and I've gifted all of my scientific files to the archive. I'm gradually breaking down current work to go into the archive. And so the letters from Bell and from Jackiw are there for credentialed historians and philosophers, scientists to look at. Okay, so this is a bit of an aside, but in order, going back now to non-renormalization, in order to make a prediction of the pi naught to 2-gamma and get evidence of what the charge counting was, you needed to know in a strong interaction theory that there would be no strong interaction radiative corrections. Now, I was convinced from the outset that the anomaly coefficient would not be renormalized just because the higher loop diagrams, those with more than 2 vector vertices. So there's the AVV diagram, which is a triangle, has an anomaly. The A4V, the shift argument works, and there's no extra term. And so I was convinced that when you connected those 2 extra vertices with a virtual propagator, that result would be preserved. And that turned out to be correct. I mean, I pursued this in a well-known paper with Bill Bardino. It was a very nice collaboration. We showed by a number of different ways, first in spinor electrodynamics, but also in the sigma model, where Bill was an expert in how to renormalize the sigma model. And we showed by a formal regulator argument and then by concrete calculation, just calculating the vertices. And then he had a clever integration by Parks argument also. So he had a bunch of different arguments to show that the higher order corrections to the anomaly coefficient will cancel around the loop. That was later verified by other people. And then eventually it became a non-perturbative result, a result of work of Tony Z, Lowenstein, Schroer, and others. Just using the Collins and Manson equations, you can prove anomaly renormalization. I'm getting a bit ahead now. What happened, though, after Bill and my article came, was that Johnson and Jackiw still contested that an unambiguous calculation is possible. Let me get some water again. I'm up in Aspen, and it's very dry here. a student, Siddhartha Sen of Ken Johnson, did a calculation for massless electrodynamics and claimed to show that there was a anomaly renormalization. Now, the problem with massless electrodynamics, although there are a lot of simplifications, you also have infrared divergences that get much worse. So that required a long and very arduous calculation that I did with Brown, Wong, and Bingman Young. There's four of us working and trading notes back and forth. So it was very complicated algebraically. And I remember a long meeting in the screen portion of my new house, and you and Princeton whether going over the final calculations with Bob Brown. So the result was, if you do the infrared part right, the anomaly still canceled in the massless theory. And eventually, now that's accepted, and in fact, it's known that the anomaly is basically of topological origin. There is a nice here by Fujikawa showing that it comes from basic regularization of the integration measure and a path integral formulation. There are papers of Witten and other people. So these are all referenced in my Selecta. There's a lot of reference to papers of other people. And that's kind of where things were left in terms of the axial chiral anomaly, I like to call it, or axial chiral anomaly, the pi naught to 2 gamma decay, and the charge counting. The charge counting, of course, leading to Gelman, Bardian, and Fritsch, and then the introduction in a later paper that Gelman saw that you needed a triple of quarks, and then it became obvious that you wanted to couple them to SU3 as in that Blue model, and QCD took its form. Okay, let me go. What's on next in the Selecta is much later. At that point, I basically left anomalies. Much later, I got into the trace anomaly because I was asked to review a paper by Iwasaki, which established an analog of the Sutherland-Veltman theorem for the trace of the energy momentum tensor. And I saw, well, if you can do that, then you should be able to turn that into a all orders calculation for the trace anomaly. And my first attempt at that wasn't right. There were some mistakes that were pointed out by Baki Beg. But during the summer of 1976, I think it was, when I was visiting almost all of them, yeah, I'm going. Let me go back. I'll come with the trace anomalies. I'll go through the Selecta because there are other things. I have a long discussion of point splitting calculations of the anomaly. Basically, after my paper in Bell-Jackiw came out, the meaning when other people showed that if you do point splitting, you get a rather simple derivation of the form of the anomaly equation. If you separate the points in the axial vector vertex with a line integral to a Wilson line to restore gauge invariance. It wasn't called the Wilson line, but they called the Wilson line. And I discussed it. The Schwinger did it, but Schwinger really was trying just to show there's no problem. And there is a problem. The significance of the axial anomaly is that you can't simultaneously assert or impose vector gauge invariance and axial vector conservation in the normal form. There's a conflict. It's like a square peg going into a round hole. You can have one vector vertex conserved or two, but not the axial, or other combinations. Now, I had no worries about this because since I did my calculation from Rosenberg's formula, and I knew I was dealing with photon processes. Photon processes have to have vector gauge invariance to make sense. And I knew that Rosenberg had done his calculation by simply imposing gauge invariance to infer the two divergent amplitudes in his calculation from the convergent ones. And so there was no doubt in my mind, you just had to impose vector gauge invariance for the two vector vertices. All right, let me go in order now. There's the non-abelian anomaly. I already at that point had some notes. This is in the 68, 67, 68 on higher loop diagrams. And I thought there might be anomalies in higher loop diagrams. And I suggested that as a problem to Bill Bardeen after we finished our renormalization calculation. And in the notes, there was a suggestion, quite prescient by Roger Dashin, that maybe you should put in charge structure to get the anomaly, to see which higher loop diagrams had anomalies. And that turned out to be very foresighted. Bill didn't remember seeing this in notes, but he interpreted whatever he did to start as being he should look at non-abelian gauge theories, which he was an expert in because he'd been worked before with Ben Lee. So he did a calculation including the non-abelian case, which of course has a charge structure built in, an internal symmetry charge structure, and came up with a beautiful formula for the axial anomaly in the non-abelian case. He had a classic calculation. It had lots of terms, and then saw that many of them could be eliminated by regularization, by polynomial shifts. But there was a residue left over, which was the anomaly. So that was a classic paper that came out essentially just after, shortly after our calculation on non-renormalization. So I'm rather proud that I think a lot of the theory of axial anomalies, chiral anomalies, came out of the Institute in that year of 1968. Okay, let me go. I want to look again. '68 to '69, I should say. Okay. I'm not going to. There are a lot of references now to follow up in this. Read my anomaly article about how the higher loop anomalies turn out to be all predicted by the pi naught to 2 gamma, the triangle anomaly. And this ties in with the Weston-Mino Lagrangian and its reinterpretation by Ed Witten. And it ties in with a calculation I did with people at Fermilab when I was visiting Fermilab, Adler, Ben Lee, Treeman, and Z, calculating some of the higher loop processes from the pi naught to 2 gamma, from the triangle diagram. So, and getting relations between the coupling constants. So there's essentially a hierarchy of anomalies, but they're all basically determined and coefficient-wise by the original triangle anomaly. Now, at the same time in '68, I did another radius correction calculation while finishing the paper with Bill Bardeen on perturbative corrections to scaling. This was done with Wu-Ki Tung, and we wrote a paper showing that the Callan-Gross relations for spin-and-a-half quarks, which asserts the vanishing of q squared times the longitudinal cross-section, gets logarithmic corrections when you calculate radius corrections. And if I recall correctly, I was sort of lying in bed with the flu when I was reading the Callan-Gross paper and thought about that, the idea of doing that calculation. I did it with Wu-Ki Tung in the vector case, gluon case, and then we also did scalar and pseudo-scalar gluons and did some fourth order stuff. There was a longer paper by Wu-Ki and me, and then he wrote it. Now that stuff was all systematized later by the Collins-Mansu equations, which give you well-defined formulas for the logarithmic corrections in terms of these various coefficients, beta and delta, of the coupling that appear in the Collins-Mansu equations. Trace anomalies. Okay, there's where I want to come to the Iwasaki paper. I was sent in 1977 a paper by Iwasaki, as I said earlier now when I went out of order, getting an analog of the Sutherland-Feldman theorem for the trace of the energy momentum tensor. And I thought, hey, that should make it possible to do something similar to what you do for pi naught to 2 gamma and get an anomaly formula and get it exact to orders in the coupling. I wrote an initial paper which had an big point. And then over the summer at Los Alamos, when I was working in E division for a month, I collaborated with John, with two of our postdocs, Anthony Duncan and John Collins, who was at Princeton. John was at Princeton and Tony Duncan was at the Institute, doing it correctly. And so we got a formula for the trace of the energy momentum tensor. This is now in QED. Here's the trace anomaly formula. You see, it involves the mass term n minus 5 r psi, but it's the correction delta and alpha, which is one of the coefficients that comes into account in that equation. And there's a term of f squared, the field strength squared, which has the beta function as a coefficient. That's very significant. That then this formula was then generalized by Collins, Duncan, and Yogalakar. Yogalakar was another institute, Satish Yogalakar institute member, to the non-abelian case. A similar result was done by Nielsen. And you get the beta function as a coefficient, and then that fed into using the trace of the energy moment tensor with the beta function coefficient to getting radiative correction improved effective Lagrangians for QED. That's Pagels and Tabulas in particular, and Safady. And they give you nice bag models for confinement, which is another story. And that's what I eventually got into in the 80s, was a long calculation as people ran, analyzing these bag models and showing that they give you confinement in QCD and in abelionized QCD, and that it's actually semi-quantitative. The abelionized, the Lagrangian you get from the beta function argument of Pagels and Ambulas is simply f mu nu times log f mu nu over a dimensional quantity. And that has the property that it confines quarks. If we do just that with the abelionized quarks, you find that instead of the flux lines spreading off to infinity, they form a bag, a kind of fat bag. It's not as tight a bag as you get predicted by lattice gauge theory. Okay, that brings me to the end of what's in my chiral anomalies in my Selecta. I mean, I didn't really work again on anomalies until much later in the 2000s, when I was interested in the possibility that spin-3 halves theories might play a role in certain ground unified models. And that required me to go back to the question of what's the anomaly in a spin-3 halves theory. And there are surprising things that came out of that. I won't discuss them more, except to say that I drew the whole subject there in an article, an archive called Recent Path Crossings with Roman and Anomalies. That was archive 1910.04089, version 1, 2019. This is really the last time I guess I saw Roman, when I knew that there was something wrong with his health. We were at a conference in Galliano Island, which I went to with my collaborator on Quantum Foundations, Angelo Bassi. And we were interested in the people and the physics, but we went also because we were told you get there by seaplane. So I began with an anecdote about Roman. We got onto the seaplane, and Roman turned to me and said, "I know the plane won't crash. Adler and Jackiw can't die at the same time." And it was actually a memorable and somewhat scary flight, because there was a high tension wire strung over the entrance of the harbor where you go to land in Galliano Island, and the plane had to fly under the high tension wire, which is a kind of tricky maneuver, because if they're too low, it's too low, you'll crash into the water. If it's too high, you'll catch your tail on the high tension wire and crash into the water. So we had to land out there. It was a very memorable flight. And I used that as a takeoff point for an article on Roman, appreciating his work, in particular his method of calculating anomalies that was in some of his later lectures, and which I then applied in looking at the anomaly of spin-3 has, and found that the only theory of spin-3 has in which the perturbative anomaly could be calculated is one where the spin-3 has is coupled directly to spin-1 half. Gave you a different anomaly coefficient counting from the standard literature, which is a curious result. It meant that a unified model with spin-3 has not to have extra fields. And eventually I didn't find the whole thing very convincing, although it's led me to believe that perhaps it's time to go back to think about composite models for particles, because we're not finding supersymmetry. And somehow, to me, the couplings to the Higgs smell to me somehow wave function overlaps of composite Higgs with composite quarks and leptons. But so far, I haven't done anything with that idea. But I think it may well be that nature is not kind, and that we've been very lucky in unearthing one kind of closed layer of the onion of particle theory, but the next layer may be a layer where quarks and leptons are composite at much higher energies that we can easily access with accelerators. So since that's kind of daunting, I don't know what to do with that idea at this point. The last few years, I've been working on astrophysics and cosmology, on ideas about black holes, galaxy formation, stars, and so forth, and also ideas for novel ideas for the cosmological constant for dark energy. In between, I did a lot of work with Angelo Bassi and his group on the Girardi-Rimini-Weber Pearl idea that nonlinear modifications of the Schrödinger equation with a small noise term give you objective reduction models that solve the quantum measurement problem. So that's a rundown about anomalies, what I did, what I haven't worked on. And at the moment, as I say, I've switched to a different bulletin archive. I was a bit surprised to find when someone asked me for an endorsement for the HPH archive. I'm not allowed to endorse that anymore. I haven't published on HEP, PH or TH for several years, and they now require endorsers to have very recent papers. So I can, it's really somewhat strange at this point what the rules are. They're making it very hard for people to get onto archive if they haven't gotten in through their thesis advisor. Okay, I will leave that. I'm lobbying a bit now for some changes in the archive rules, but it doesn't affect me because I've been published a lot on GRQC, and all my stuff on astrophysics and gravastars and dark energy goes there. Okay, I can open this up for questions now. I think the bottom line as far as the history is, I think people who want to learn the history of the Chiral Anomaly should go back and read the original papers, not subsequent lectures, which of course combine everything that everybody did, but the original papers by me, by Bell-Jackiw, by Bill Bardeen, and other people who are major contributors. Okay, thank you.
Thank you very much. So for
now, was it first of all, was it legible? I had problems with another Zoom, but I think your connection is better.
Yeah, it was legible.
Okay.
Yeah, thank you. So I was wondering about you were about Schwinger and
yes.
Sort of the point splitting calculations of the anomaly. I was wondering if you could say some more about that and sort of what exactly he missed in trying to.
Yeah, this is an equation. This is discussed in detail in the get it in the 50 years, the article I wrote for 50 years in the Yang-Mills series, and it's discussed somewhat more briefly in my Selecta. What he did was do point splitting. What he did was to transpose the anomaly term into a redefined axial vector current. And so he said, well, everything's okay. The pseudo vector is equivalent to the pseudo scalar. But he kind of buried the anomaly under the rug that way. And he and his group never accepted the non-renormalization. I had disputes with the people who were in his Los Angeles group. And the reason I wrote that was that once I visited the University of Washington, Lowell Brown had put up a big display about how Schwinger discovered the anomaly, which I thought was a bit churlish for him to do, but I don't know, it had to be rebutted. And so I addressed that directly in my anomalies to all orders article. So if you look carefully, let's see. So I have a section 2.3. This is in archive HEP TH 0405040040. That was the article from Gerard Hoof's book on 50 years of Yang-Mills theory. And what I showed was he essentially evaluates the effect of Lagrangian in which he's transposed the anomaly equation to the left-hand side. And so point splitting turned out to be useful, but Zumino and others made very neat calculations of the anomaly once my paper and Bell-Jackiw came out. But what Schwinger and other people didn't do was to observe that you can't make the axial vector matrix elements satisfy all of the expected symmetries. He said everything's okay if he just point split. Well, it's not. As I said, it's like a square peg in a round hole. You can calculate the triangle diagram to make the vector vertices or to make an axial vector vertex conserved and the vector is not, but you can't make all three conserved. And so that was kind of hidden in what Schwinger did. So I would say Schwinger did not discover the anomaly. Discovery occurred much, and all the follow-up papers by other people occurred in 1968 with my paper. Does that answer your question? I think I said a bit about this also in my Selecta article, but not in quite the detail as in the article in Gerard's book.
Yeah, it does answer my question. Thank you.
Are there any other questions?
I wanted to ask a question about topological interpretation of chiral anomaly. If you could talk more about that. Thank you.
Yeah, yes. Well, I haven't brushed up on that, I'll have to say. In the non-abelian version, there's basically what Bardeen's calculation looks like, very much like as the Chern-Simon expression. And I'd have to go back and review here. As I say, I haven't thought about this stuff for ages and have been working in astrophysics and cosmology, gravitation the last few years. So when I say it's topological, Fujikawa's calculation derives the anomaly just by showing that the thing that in a regularized field theory where the naive reasoning fails is the path integration measure. And that's already not a perturbative thing. That shows why the lowest order is the exact. And then Ed Witten had various papers showing that it's basically topological. But I can't say a lot more about that without going back to some of the papers on it. Now, the anomaly has an interesting consequence in condensed matter physics, which is the Nielsen. You'll have to help me with this. I'm sorry, the name is jumping out of my head. Those papers, but there's a curious. They're nice experiments now showing that in Weil semi-models, you get a solid state analog of the anomaly. And I'm afraid I'm a bit lost for words now because I haven't reviewed this.
Thank you so much.
Yeah. Any other questions? Okay, should I leave the meeting or should I wait a little bit more?
No, yeah. Thank you very much for being here.
But let me go back to one thing, which is this little remark I made in my adventures with theoretical physics. I'll show you this section. And this is again happening in what I'm doing currently. I have in section 10, we are next, page 1. I'll just read you a few lines of that. I said, in looking back at my work, I see one pattern that is repeated over and over. Many of the most interesting research results that I have obtained were unanticipated consequences of other quite different research programs. In the course of detailed calculations or speculative explorations, I noticed something that seemed worth pursuing, even though tangential to my original motivations. And this new direction ended up being of much greater interest. And so my advice to young people and to myself is don't sit around waiting for a great idea. Just sit down and calculate something and keep your eyes open. And often something surprising will emerge from it. Okay. Thank you.
Thank you very much.
Bye-bye.